All right, so we're going to talk about energy now. We've got a whole chapter devoted to energy, and there's lots of terms in this chapter, and most of the terms are going to be terms you've heard before, but not necessarily in this context, and they all sound so similar. So that's the challenge, I think. So get several sheets of paper out, get a pencil ready to go, and start taking notes, and then use these notes as you're studying and doing homework. Feel free to look back at your notes, and the more that you look at these terms, the more comfortable you'll be. So let's get started. So first of all, you can appreciate that chemistry is devoted to changing and the energy changes that are associated with changing in materials, right? So that's a big part of chemistry. Well, it turns out the energy changes we're going to lump into a category called thermochemistry or thermodynamics. Thermodynamics is the study of heat absorbed or released during chemical or physical processes, right? So thermodynamics or thermochemistry is what this chapter is all about, and it has to do with the energy changes of materials. So energy, let's define that real quickly here. The energy is the capacity to do work, essentially. Usually that's what that's called. So all supplying heat, your textbook author includes that in this. Energy is the capacity to do work or to supply heat. It turns out those two are equivalent. So that's why we oftentimes just shorten it to energy is the capacity to do work. Now there's two main types of energy, potential energy and kinetic energy. Potential energy is the energy of position, right? Some people will include composition and condition, although those are sort of energies of position as well, which we'll describe more later. Potential energy is the energy of position, and kinetic energy is the energy of motion. All right, and these two can be interconverted. So, for example, if you've got water, here's water at the top of Victoria Falls in Africa. If you have water at the top of the falls, it has a high potential energy. As it falls, it's converted into kinetic energy, and when it gets to the bottom, it makes a lot of heat, and it's converted into it's converted into heat at that point, right? So it has low potential energy in the bottom, high potential energy at the top, low potential energy at the bottom, and it's converted into heat by way of kinetic energy and collisions as it gets to the bottom. So water also flows, for example, through the Hoover Dam. You've got water that flows through the dam, and it turns turbines and converts potential energy into kinetic energy, which is in turn converted into heat and electrical energy. So there's a couple ways that energies are converted, one between another, and this I think takes us to an very important principle in physics, which is called the law of conservation of energy. Law of conservation energy essentially says energy can be neither created nor destroyed, although it can be converted from one form to another. So let's talk about some more terms. Now, thermal energy is a type of kinetic energy, and it's associated with the movement of atoms or molecules or small particles, okay? So that's what's thermal energy. Temperature is a quantitative measure of hot or cold. So if you have really fast-moving molecules, you might say that material is hot. If you have slow-moving molecules, you might say that material is cold. All right, and that we say hot or cold, we think of in terms of temperature, but it turns out a high temperature means a high thermal energy, and low temperature means a low thermal energy. So here's a couple pictures that might demonstrate that. If you have water molecules, let's let each of these spheres just represent a water molecule. If it's moving really fast, we'll say it's a red water molecule, and that's sort of what these little, lines are around these things. We're saying that the water molecule is moving really fast. If it's moving really fast, we'd say it's hot. If it's moving really slowly, we'd say it's cold. If it's moving slowly enough, then it turns out it doesn't have any translational motion. It's just vibrating back and forth. We would call that ice. All right. So heat now. Here's another term which we're going to use in a technical sense. This is a Q. You can't see it because this is a Q. So the symbol we're going to use for heat is going to be a Q, and heat is the transfer of thermal energy between two bodies at different temperatures. Heat flow, actually heat is a flow, right? Because that's the transfer of heat. So heat flow, it's a redundant term, it increases the thermal energy of the colder body at the expense of the thermal energy of the other body. In other words, thermal energy will always flow from the higher temperature to the lower temperature, right? Heat flow will always go, and it's always going to do that until both bodies achieve the same temperature. All right, so here's a pictorial example. If you have hot water and cold water and you allow them to come into contact, then the heat is going to flow from the higher temperature to the lower temperature until they both have the same temperature. And when they're the same temperature, we would say that they were in thermal equilibrium. All right, so an exothermic process is a process that releases heat, right? And you might remember that by thinking of exo as an exit, okay? So if a process releases heat, we would say it's exothermic. If it absorbs heat, we would say it was endothermic. Right, so a couple examples of exo and endothermic. Exothermic is if you have, say, a torch here. This is an oxyacetylene torch, where acetylene's coming in one pipe and oxygen's coming in the other pipe. They're mixed together, and it just releases a tremendous amount of energy. This is exothermic, right? And another process, you might have a cold pack, which has water inside, ammonium nitrate here, and if you break that cold pack, then the ammonium nitrate begins to dissolve in the water, which is a very endothermic process. It takes heat out of the air or out of your hands or your ankle or wherever you're putting this cold pack. Okay, so let's introduce now to the units that we use in heat. The units that we use in heat are calories. Historically, were calories, right? Where 1,000 calories we would say is a kilocalorie, or we might write that with a capital C. The food that you eat, when you talk about the certain amount of calories that you're eating, those are actually capital C calories. Those are kilocalories. That's 1,000 of this calorie that we use with a lower c. Okay, lowercase c. Now, the more common unit that we use now is joules, and it turns out 1 calorie is equal to 4.184 joules. All right, they're both units of energy. Joules is going to be the one we're going to use more commonly, but you have to watch out. Occasionally, calorie slips its way in, which is fine. It's just a conversion, right? It's like using, I don't know, meters or yards or inches or centimeters. You can deal with both. So a joule is defined as the amount of energy used when 1 Newton moves an object 1 meter, Newton meter, okay? So that's the definition of a joule, a Newton meter. Okay. So heat capacity now, and we're going to use a capital C for this. Watch out. If you Google this, you're going to find that people use different symbols. And you'll find some great resources if you Google it. But capital C is what we're going to use in this textbook. Lowercase q is what we're going to use for heat. Remember that? So the heat capacity is the amount let's see. The heat capacity, Q is equal to MC delta T. Let me just say that. The heat capacity is defined as you know what? Let me just leave it at the formula, okay? My vocabulary is really, yeah. So the heat capacity is defined in this way. So if you take a certain amount of mass, its heat capacity, the change in temperature, that's how much heat that you get out, okay? I'm just going to read this to you. This is what I've got it here, right? The heat capacity of a body of matter is the quantity of heat it absorbs or releases when it experiences a temperature change of 1 degree centigrade, or 1 Kelvin, right? Heat capacity is an extensive property because it depends on the amount, right? For example, the heat capacity of a large cast iron pan is greater than the heat capacity of a small cast iron pan because there's more to it, okay? So specific heat capacity now is intensive property, and it does not depend on the amount because it's defined by 1 gram. The specific heat capacity, we'll use a lowercase c for that, is defined by the amount, let's see, of a substance commonly called specific heat is the quantity of heat required to raise the temperature of 1 gram of the substance, right? So that's an intensive property because we define it by 1 gram. Now, if you Google this, you're going to find some great resources on it, and a lot of times people use SH for this instead of a lowercase c, okay? So it doesn't matter. To me, it doesn't matter. Hopefully it doesn't matter to you, but just watch out for that. Be careful. If you lose what these symbols mean, you know, you could be in trouble. All right, so specific heat's an intensive property because it's defined by 1 gram. All right, and so the specific heat of a large cast iron pan and a small cast iron pan are the same. So a couple cast iron pans here. The heat capacity of the bigger one is more, but the specific heat of them are the same. All right, so here's some specific heats of some common substances. Okay, and kind of interesting, look down here, look how low these specific heats of lead and gold are. I mean, it takes a lot of energy to raise these 1 degree centigrade. But this one, like, that's got a high heat capacity, which is really nice. If you live by the water, then that means that the temperatures are modified greatly because the water is taking in so much heat, and it's a big heat reservoir as well, right? So when it gets really hot, the heat goes into the water, and it keeps the land cool. And when the temperature is really cold, then heat comes out of the water, right, and modifies. This is really nice. Thank God. All right, so let's talk about calculating heat. The amount of heat required or leaving a substance can be calculated in the following way. If a substance gains thermal energy, then Q is positive. If it loses thermal energy, then Q is negative. And let's look at a specific example, okay? So a flask containing 800 grams of water, 800 grams, oops, it's two sig figs, okay, right? I put that dot there, I shouldn't have done that. It's 2 sig figs, you see that? 800 grams of water is heated, and the temperature of the water changes from T1 is equal to 21 degrees centigrade. T2 is equal to 85 degrees centigrade. And delta T is equal to, looks like that's 64 degrees centigrade, right? How much heat did the water absorb? Well, we know that Q is equal to MC delta T, right? That's a capital C, doesn't look like it. And the mass is 800 grams. You know, I'm going to do a different color here. I know I'm trying to go fast because I don't want to drag this conversation out really long, because some of you are sort of cruising through. No, let's go back to red. 800 grams, watch this, and C, I got to look that up. Remember the specific heat, remember the heat capacity of this? The heat capacity is 4.184. You know, this is specific heat here. I used the wrong symbol. I warned you about that, and I just made that mistake myself. 4.184 joules per gram degree centigrade. Let's go back here. This is specific heat, which is lowercase c. Yeah, I used the right symbol, but I thought it was, yeah. Meant to write a capital C, actually wrote a lowercase c. Anyways, that's the symbol we need, is joules per gram degree centigrade. This is going to work out beautifully. And look at this. This is degree centigrade. This is 64, right? And this is 800 times 4.184, because I just looked it up on a previous slide, right? I'm going to pull my favorite calculator out here. I love my calculator. You know why I love it? Because I use it, and because it gives me lots of right answers. You should use your calculator too. Use it. Love it. Marry your calculator. Times 4.184. They'll be a little difficult. Calculators are pretty reliable, but I wouldn't trust one for better or for worse, right? Okay, and I get, oh, grams cross off, degrees Celsius cross off, and I've got joules, right? So it looks like it's 2.14822, and so on, times 10 to the 5 joules. I'm going to change this to kilojoules, and I'm going to take into account my sig figs. There's 2 sig figs here, and there's 2 sig figs here. Perfect. So it'll be 2 sig figs in my answer. Looks like it's going to be 2.1 times 10 to the, and I'm going to do this part in my head, times 10 to the 2 kilojoules, and that's the heat that I get. All right, from that. Okay, probably should go check this in case I made a mistake, but I'm going to leave it like it is, and I'm going to finish this section out with a nice figure from our textbook, which shows a couple pictures of the Ivanpah solar thermal plant that uses 170,000 mirrors to concentrate sunlight on water-filled towers. Very cool. We're going to heat the water up by using these mirrors. It covers 4,000 acres of public land in the Mojave Desert, and it's a great example of how we can take sunlight and heat water and get energy from it. So, all right. I hope this wasn't too fast or too slow. Good luck with your study in energy of chemistry.